Before I look at the problems, I should show you again something I showed last time, something you might find useful in Physics 184 or 234. There are some video screencasts at YouTube which provide an introduction to the subject for each week. So here's the YouTube channel. If you go to YouTube and then you do a search on Physics 234B of Professor Stump, it should take you to this YouTube channel. It says 234B, but 234B and 184B are combined this summer, so it's just as appropriate for 184. And I think for each week there are two videos which provide an introduction to the subject for that week. They're not really a substitute for reading the textbook. They're just kind of to get you started. So this is optional, but it may be useful. Watch the screencast at the beginning of the week. Read through the chapter, or at least glance through the chapter, and start doing the long kappa problems. So check it out. Go to this channel. Click on playlists. There are two playlists. One playlist has the screencasts. The other playlist has recordings of the Zoom meetings. So choose the one which says Summer 2021 and find the chapter that we're working on. You know, this week, I guess it's chapter 21. And you see there are two screencasts with information relevant to chapter 21. Now, if you get stuck on the homework after you've sort of looked over the chapter and you've watched the videos, if you're stuck, if you can't figure out what equations to use, well, I would say when you watch these screencasts, you should take notes. Have a notebook handy, take notes, then you'll have the equations that you need when you start doing the long kappa problems. But if you get stuck, then read the relevant section in the textbook. Or there's a file full of online lectures at Lon Kappa. So open up the online lectures file, find the chapter that we're working on, try to find the lecture which is relevant to the problem you're stuck on. Probably easier to look in the textbook, but some people don't like to read. Some people would prefer to hear something explained. So either of these two should get you unstuck. And there's another good way to get help on the homework. Submit a question to the discussion board. On Lon Kappa, you can click on the little icon for the discussion board and type a question into the discussion board, and then hopefully somebody else will see your question and answer it. But don't submit questions at the last minute, because if you submit questions just before the homework is due, well, maybe nobody's looking at the discussion board at that time. All right, so we want to look at a couple of problems. So here's one of them. This problem. We're studying the forces between charges. And, you know, a lot of the problems involve two particles or 2 point charges, or maybe a few particles. And that's pretty limited. What if you have objects which are not particulate, you know, which are not small spheres, but some kind of extended object with charge on it? So this problem is an example of that. A charged rod and a charged particle. So here's the charged particle, Q, And here's the charged rod, which has a total charge capital Q. So Q is 2.3 C, little q is 1.4 C. And of course, the question is calculate the force. What's the force on this particle? And you can sort of guess. It's going to be, these are both positive, like charges repel. So Q will be repelled from the rod. It'll be repelled more strongly from these points, which are close to Q, more weakly from these points, which are far away. So you might expect the force will be something like that. It'll have a negative X component and a positive Y component. Well, that's what you're trying to calculate, Fx and Fy. Now the method, when you have an object which is extended in space, not just a single point, then you use the method called superposition and integration. This is explained in that YouTube video, the video chapter 21, part 2, explains how to do problems like this. I think it explains this problem, or anyway, something very much like it. But I'll go over that tonight anyway. So, okay, so here's what you need to calculate forces. You need the fundamental equation for the force between charges. That's called the Coulomb force, named for Monsieur Coulomb, who measured it first. If you have 2 point charges, a point charge capital Q and a second point charge little q, then the force on, let's say that we're trying to calculate the force on this smaller charge, it's KQQ over r squared times r hat. Of course, force is a vector, so it has to be a vector. Its magnitude is KQQ over r squared. It has to have a direction. So it's that magnitude times a unit vector, r hat. And r hat is a unit vector, so r hat is r vector divided by the magnitude of r. And what's r? Well, r is the vector. Draw a little picture here. Here's q at some point in space. And here's little q at some other point in space. And here's r. R is the vector from capital Q to little q. So that's xq minus x capital Q. You know, someplace you have an origin, if you go to Q and then you go across R, you end up at Q, little q. So R is xq minus xq. This constant, k sub c, it's sometimes written as 1 over 4 pi epsilon 0. That's a universal constant. It's just a constant of nature. Depends on the units that you use. In our standard units, it's approximately 9 times 10 to the 9th. Now, actually, it'll be easier to calculate forces if I rewrite this in a different way. R hat is a unit vector. So it's the vector divided by the magnitude of the vector. And R without a vector symbol is the magnitude of the vector. So F is KQQ R vector over R cubed. Or KQQ x minus x prime over x minus x prime cubed. Where here x is the position of Q, that's xq. X prime is the position of capital Q. That's x capital Q. So that's the force on little q. That's just 2 particles. Now, if you have many particles, if you have a system with many charges, let's say you have a whole collection of charges, let's label them, or let's give them the values delta q and locations x prime, and then a point charge q, little q. then the force on little q is the sum of the Coulomb forces due to all the many charges acting on q. So that's this Coulomb force, k q q, k delta q q, x minus x prime over x minus x prime cubed, where delta q is one of the charges, x prime is the position of that charge, and I have to sum over all the charges. So you should know this notation. The Greek letter sigma, Greek letter capital sigma, means sum. Well, that's superposition. And you have quite a few problems on the log kappa assignment which involve superposition. But now integration. When the charge capital Q is an extended charge distribution, like for example here, capital Q is a rod. It doesn't have a position. It has a whole bunch of positions. It's stretched out along the x-axis from the origin to a point at distance L from the origin along the x-axis. So there is no position for the rod. It has an infinite number of positions because all the points on the rod have charge. So you have to sum over all the points on the rod this quantity. But you know what happens when you add up an infinite number of contributions, an infinite number of infinitesimal contributions. That's the integral. So that's integration. So we replace the sum by an integral. The function is the same as before. K, only instead of delta Q here, we write dQ, the differential part of the charge, times Q, that's the test charge, times x minus x prime over x minus x prime cubed. Next week, we're going to find that the electric field is exactly this quantity divided by the test charge. So I'm tending to think of this little lowercase q as a test charge, a probe. And if I divide by the probe, then I get the electric field, but that's for next week. Now, Kc is a constant, so I can bring it outside the integral. Q is a constant, so I can bring it outside the integral. Then I've got x minus x prime over x minus x prime cubed dq. So that's the fundamental formula for the force on a point charge Q located in the region of an extended charge distribution. All right, so let's go back to this problem. We're going to apply this fundamental equation to this problem, the rod and the particle. Well, a rod is not a single point, but it can be thought of as a collection of points. I can subdivide the rod into many small pieces. Subdivide the rod into 1,000,000 parts. Each little part is a particle. And I already know how to calculate the force due to the particle. So now I just have to integrate over the rod. So each point on the rod, let's say this little point here on the rod, this little section of the rod, which is this distance from the charge, from the test charge, exerts a force. I guess it's maybe this force. And this part of the rod exerts this force. And this part of the rod over here exerts this force. So in fact, if I've got 1,000,000, if I've subdivided the rod into 1,000,000 parts, I have to add up 1,000,000 forces. To add them as vectors, because force is a vector. But I don't have to add up 1,000,000 things. I just do an integral. So here's the fundamental equation. It's Coulomb's constant times the charge of the particle times the integral x minus x prime over x minus x prime cubed dq. And it's only a question of calculating that integral. Now let's see how we do that for the exercise. F is a vector, so I'll have two components. I'll call them fx and fy. And x minus x prime is a vector, so it'll have two components. It'll have components x minus x prime and y minus y prime. Everything takes place in the xy plane, so there's no z in this problem. So this is the x-axis. This is the y-axis. This point is at point xy. This little section of the rod, that's delta q, is at the point x prime, y prime. So I have x minus x prime, that's the x component of the vector, and y minus y prime, that's the y component of the vector. Now, x and y are the, well, xy is the position vector of q. And you can see from the picture here, it's 0, L. If you count here, 1, 2, 3, 4 boxes is the same as 1, 2, 3, 4 boxes. So this is length L, then this distance has to be L. So xy is 0, L. And x prime, y prime is a point down here. Let's put this point here is going to be dq. What are its coordinates? Well, it's x prime 0. It's some value of x. It's some value on the x-axis. I'll call that x prime. And it's at y equals 0. So y prime is 0. All right, so that takes care of this. That takes care of this. What about r? R is this distance. By the Pythagorean theorem, r will be x minus x prime squared plus y minus y prime squared. So I'll come back to r in a minute. What's dq? Well, I'm assuming that the charge is uniformly distributed along the rod. So how much charge is there in this little section of the rod? That little section of the rod has a length dx prime. How much charge does it have? Well, it's some fraction of q, capital Q. It's the fraction of q equal to the fraction of the length. So the fraction of the length is dx prime over L. That's the fractional part of the rod. And that times q gives me dq, the amount of charge in that little section. Or I could write this as q over L dx prime. So see, I'm going to integrate along the rod. I'll have an integral dx prime. All right, now let's go with f sub x. There are two calculations to do here, f sub x and f sub y. Well, let's do f sub x. And then you'll have to go home and do f sub y. But they're both done in the same way. We have this constant kc times q, and also another constant q divided by L. So I'll have kc times q divided by L. Those are all constant terms, so I can pull them outside. They just multiply the integral. Now, what's the function? Well, for fx, it's x minus x prime. It's 0 minus x prime. So it's minus x prime. And then dq gives me dx prime. And now what's r? Well, r squared, well, look at this little right triangle here. R squared is x prime squared plus L squared. But this is r cubed. So this will be x prime squared plus L squared to the 3/2 power. This integral is elementary. I'm sure you can do that integral just with a piece of paper. Last week, I showed 3 methods of calculating integrals. And you can apply any of those 3 methods to this integral. But probably for this one, the easiest way is to just do the integral by pure mathematics. It's an elementary integral. The integral here is 1 over x prime squared plus L squared to the power 1/2. Maybe times some constant. But you see, if I differentiate 1 over x prime squared plus L squared to the 1/2, I'll get 1 over x prime squared plus L squared to the 3/2 times the derivative of x prime squared, which will be 2x prime by the chain rule. So I've got exactly this function. So the integral is elementary, and don't forget to evaluate it at x prime equals L minus the value at x prime equals 0. Now, when you do that integral by any of the 3 methods that I described last week, what you'll find has this form. It'll be KQQ over L squared. Here's the KQQ, it's already there. Here's a 1 over L. Well, there'll be another 1 over L. And then what's left is a pure number. Just a number with no units, no parameters, just a pure number. There's one last step, and that's to use your calculator. Ln kappa will require you to put in here a digital number, a decimal number. So you have to multiply these various quantities together. You can just do that with a calculator. Or you could write a little computer program to do it if you're good at programming. Probably the easiest is just use a calculator. That's fx. I have to do the same thing for fy. So there will be 2 answers to this problem. Well, the only difference is instead of x minus x prime here, I'll put in y minus y prime, which is just L. So just have L dx prime over x prime squared plus L squared to the 3/2 power. Actually, that was one of the integrals that was on the first homework assignment. I would say 99% of the students got the first homework, got that problem on calculating integrals in the first homework assignment. So again, you can use any of the 3 methods that I showed last week. So that's a good example of superposition and integration. Now, before I go on to the last problem, are there any questions? All right, well, the last problem is, again, a problem with a charged object. So we have a little point charge here. We'll deal with this kind of problem with point charges next week because the electric field is the force on a point charge divided by its charge. So this is like a little probe, Q. And here's Q. So this disk is the charge Q. And we're assuming that the charge is uniformly distributed around the disk. So every point on the disk is a little part of the total charge Q. So each little section of the disk is an amount dq. So here's a little part of the disk. It's a little section of an annulus. An annulus is a ring with a thickness. So it's kind of got a radius. It's actually got an inner radius and an outer radius. So it's got two radii. It's got a little bit of an angle. And that makes a certain area. And dq, the amount of charge in that little area, will be equal to the charge density, the charge per unit area, times the area. Now, what's the area of this little section of an annulus? Now, here's a little section of an annulus. It has one dimension is the radial dimension, length d rho, where rho is the distance, put it a different color here. Rho is the distance from the center of the disk out to this point. It's a length. It's a radial length. It's not this radius. That's r. It's this perpendicular distance. That's rho. So, you know, one dimension of this little section of an annulus is d rho. And the other section is rho d phi, where d phi is the angle in radians. That's a definition of radians. If you take a radian measure times the distance from the center, that'll be the arc length. So the area is L1 times L2. So it's d rho times rho d phi. All right, so now we apply the method of superposition and integration. So again, we have this fundamental equation. It's kq integral x minus x prime over x minus x prime cubed dq. Now it says in the problem, by symmetry, the force on Q will be in the z direction. You know, this disk is in the xy plane. Different points around the disk will produce forces in different directions. But if I add them all up, the net force will be in the z direction by symmetry. There's a kind of cylindrical symmetry here. So the x and y components of the force will all cancel out when I combine them. The z components will all add up. So I really just have to look at the z component, Fz. So it's kcq integral z minus z prime over r cubed. dq is sigma dA. Now what's z? Well, z is the position of the test particle. So that's z. Z is the height of the test particle above the xy plane. And what's z prime? Well, z prime is the position of this little section of the disk. That's 0, because the disk is on the xy plane where all the coordinates of z are 0. So z prime is 0. Now what about r? Well, this is z. This is the center of the disk. This is rho, the distance out to this part of the charge. And this is r. You can see from the Pythagorean theorem, r squared is rho squared plus z squared. And I also have dA. What's dA? Well, I figured that out over here. It's d rho times rho d phi. So it's d rho times rho d phi. So if I put everything together, f sub z when the test particle is at z is kc times q integral z minus z prime will be z minus 0. So it'll be z over rho squared plus z squared to the 3/2 power. That's the r cubed. Sigma dA rho d rho d phi. Now phi is the azimuthal angle. Phi is the angle around the z-axis. Since this is a complete disk, phi goes from 0 to 2 pi. Phi has to be in radians. So phi has to be 2 pi radians. So the integral over phi will be 0 to 2 pi. And as for rho, well, rho goes from 0 out to the edge here, which is the radius of the disk. So I guess it said the radius of the disk is r. So rho goes from 0 to r. Now you see the function doesn't depend on phi. That's an example of the cylindrical symmetry. So the integral d phi will just be a factor of 2 pi. And phi is gone then. So putting it all together, I got 2 pi, k, q, I got the constant sigma, the constant z, then I got the integral 0 to r, rho d rho over rho squared plus z squared to the 3/2 power. Now again, this is an elementary integral. It's something like 2 over the square root of rho squared plus z squared. 2 times rho squared plus z squared to the minus 1/2 power. Or maybe it's the negative of that. Anyway, that's an elementary integral. But you can calculate this integral by any of the 3 methods that I described last week. So do the integral. And then you'll have a formula, a big formula, and you have to use your calculator to multiply all these numbers together. Remembering that sigma is the total charge of the disk divided by the area. Sigma is charge per unit area. So a little section of the area, dA, has a charge dq. So the full charge will be the full area. So Q is sigma times the complete area. The area of a disk is pi r squared. So you've got all the numbers to plug in and calculate a number for ln cap. Okay, so I guess that's all I had prepared to talk about tonight. So let me check if there are any questions on the chat. Is the distance between Q and the origin equal to L? Yeah. I mean, look at the picture. This distance is L. It's 2.5 boxes. This distance is L. It's 2.5 boxes. What would the pure number be? Ah, well, that's where you have to do the integral. All right, so that's all the questions that were on the chat. Anybody have a question? If you have a question, you can just unmute your microphone and speak up. Don't be shy. If you have a question, you can be sure that other people also have a question.
Yeah, actually, I got a quick question for this one, just this one. Yeah, so
this
how
one
about
the charge rod?
Yeah, this
okay.
Yeah, this one you're showing. Just about what is the FY? I'm kind of confused.
I think I have to go back here. Well, here's fx. That's this integral with x minus x prime over r cubed. Here's fy. That's the integral with y minus y prime over r cubed. So fy is the y component of the force vector. Y minus y prime is the y component of the radial relative position vector.
Then to be more specific, why the Fy is not equal to Fx since the L is equal to the distance from the Q to the origin?
Well, I think you can see from the picture that they won't be equal. I mean, you're going to add up all these forces. Adding up all the y components will give you Fy. Adding up all the x components will give you Fx. Fx is going to be negative. Fy is going to be positive. So the reason they're not equal is because the integrals aren't the same. The integral for Fx is minus x prime over r cubed. The integral for Fy is L divided by r cubed. Because the y component here, y is L, y prime is 0. So the numerator here is L in one case. It's minus x prime in the case that I did.
What was Kc again?
Kc is called the Coulomb constant. If I go back to Coulomb's law, here's Coulomb's law. K Q Q r hat over r squared. Now, sometimes Kc is written as 1 over 4 pi epsilon 0, where epsilon 0 is yet another constant. Epsilon 0 is called the permittivity of the vacuum. You know, K and epsilon are sort of interchangeable. They're just related by this equation. The value of Kc is 9 times 10 to the 9th, or actually it's 8.99 times 10 to the 9th. And you get that. I mean, watch the videos. Or if you just don't have that written down from watching a video, then look in the book. It's a universal constant. It's a constant of nature. It depends on the units, so it's not just a pure number. But for standard units, it's 8.99 times 10 to the 9th.
Thank you.
Any other questions? Okay, well, I guess this assignment is due Thursday at midnight. Well, Thursday at 11:59. So you have, what's today, Tuesday? So you have Wednesday and Thursday to work on this problem, or to work on all the problems. I didn't send out any feedback for the first assignment, but I can say the first assignment, just about everybody got all the points. I don't know what the average was, but the average was certainly above 90% on the first assignment, probably above 95%. I don't actually have the number. But that was just, you know, some math problems to kind of get started. Now we start doing the physics problems. It involves the equations from the textbook. I don't know. Maybe everybody's going to get 90% on this assignment. Have to wait and see. And I think I said this last week. I'll try to have Zoom meetings like this each week. To provide hints for some of the problems. And I'll have those at this time. Tuesday at 7 p.m. And I do record the Zoom meetings, so you can find those at the YouTube channel. So if there are no more questions, I'll end the meeting.
Actually, I still got a question about the Fy. So could you please just write down it again? I just cannot figure it out.
It's just exactly like this.
Exactly like
this is Fx.
Uh-huh.
Okay. If you did Fy, it's the same, except you replace minus x prime. You replace that by L. It's exactly the same thing, but replace the minus x prime here by L.
How about the dx prime?
No, that's the same, because I'm integrating along the rod.
Oh, I see.
All right, so let's see how I end the meeting here. Okay, so I'm ending the meeting. See you next week.